Hey YouTube, welcome back to Tinkertown. Today I'm going to show you how I turn this LEGO Technic Lamborghini into a working RC car that goes 35 kilometers an hour. We're not going to need this. This is part 2 of my LEGO RC car series. To see how I painted this RC car, check out my other video linked here. And while you're there, be sure to give my channel a subscribe. In my first attempt at turning this into an RC car, I tried to use a small brushless drone motor I had laying around the house. I 3D printed a few different small pinion gears. The 2 gears on the right snapped almost immediately, but the larger gear seemed to be more durable. The small gear gave me a large gear ratio, which was needed since drone motors are very high speed but low torque. Along with this custom bracket I made, the motor and gear was small enough to fit in the rear wheel well. I powered this motor using a cheap ESC from AliExpress that was rated for 12 amps. Originally, this LEGO model only had a single axle for each rear wheel. I 3D printed a new axle to make a 2-wheel drive vehicle. I printed a clone of the LEGO axle at 5mm in diameter and just extended it long enough to connect to both wheels. I had to remove a couple parts to clear the shaft area. I then printed an 18-tooth pinion gear with a plus-shaped LEGO fitting for the shaft to secure through. I used this 3D gear modeling website, which I'll link in the description, to print proper metric gears. Gear module refers to the size of the tooth. In this case, I made a Mod 2 or 2mm sized gear. The number of teeth I chose was 18 since it was the biggest I could fit within the diameter of the wheel. Since my motor is a high-speed, low-torque motor, I needed a very low gear ratio to create enough torque to move the wheels. The gear I showed earlier was actually for a later test. I originally used a 6-tooth motor gear to get a 1:3 gear ratio. Gear pressure angle refers to the curve of the teeth on either side of the gear center line, where they contact, and dictates how well the gears roll off of each other. For RC cars, 20 or 25 degrees is common. Once I installed the axles and gears, I wired up a FlySky 3-channel receiver to control the PWM throttle. I paired the receiver with the FlySky FS i4X 4-channel transmitter. Finally, I was ready to test the whole thing out. I first tried to turn the wheels from a wireless throttle command with no load on the wheels. Overall, the test was pretty promising. The motor spun well, although the wheel needed to be secured, and the shaft was bending a lot. For my second test, I tried to put the car on the ground and drive it. This did not go very well though, as you will see.
That's it? That's it? What? Take 2.
I tried again after adjusting the gear meshing a little bit. What happened here? Well, the buzz sound you heard was the motor controller ESC burning up due to overcurrent stress caused by motor cogging. We can actually see the motor cogging shown as the jitter of the wheel moving back and forth in the no-load test. Normally, a brushless motor spins in a constant circle due to 3 phase-shifted magnetic fields in the stator pushing the rotor permanent magnets sequentially in a circle. The chart on the right shows the 3 AC voltages shifted 120 degrees apart. In phase 2, the red phase has a positive magnetic field which pushes the north pole of the rotor counterclockwise. The gray phase has a negative magnetic field which causes it to also push the south pole of the rotor counterclockwise. In phase 3, the blue phase has a positive magnetic field which pushes the nearby north pole again counterclockwise. Finally, the gray phase has a negative magnetic field which pushes the nearby south pole counterclockwise. Overall, this drives the gears counterclockwise. Cogging can happen for many reasons, though in this case it was due to insufficient torque. The applied magnetic fields couldn't move the rotor past the stator poles, so as the 3 phases changed polarity, the rotor was getting pushed back in the opposite direction, causing a back and forth jittering. The cogging essentially causes a short circuit and can overheat the motor controller. For these reasons, I decided to switch to a simpler brushed DC motor design with a much larger and more powerful motor. For the motor controller, I bought a higher current Injora MB100 20-amp ESC controller. Then, I bought a 555 sized brushed DC motor with a high-speed wiring of 11 turns. I made a 3D model of the motor and axle mount in SolidWorks, and I'll provide a link to this and all the other 3D models used in this video in the description. As you can see, the 555 motor fits in perfectly snug. I screwed the motor into the case to make sure it stays secure. Next, I created a new 30-tooth gear with a module of 1 and a pressure angle of 20 using the website I showed previously. I imported it to SolidWorks and added a spacer and flat part of the hole to match the shaft of the motor. Now I mounted the motor assembly to the back of the car. I took out most of the back LEGO parts to make this fit, while leaving plenty of spots to anchor the new motor assembly to the remaining LEGO. You can see here the 8mm hole for the axle. Here, I printed a 40-tooth Module 1 20 PA axle gear, which gives us a gear ratio of 3:4, which is more speed since the larger motor will have sufficient torque. The axle I used was an 8mm axle, which provided massively more structural strength than the previous 5mm plus-shaped LEGO shaft. Many of those LEGO shafts broke on me. I bought 7mm C-clamps from AliExpress, which were a little small for the 8mm shaft, but I bent them a little to make them work. These clamps are a common tool to keep the axles from sliding horizontally, which among other things would misalign the gears. With the drivetrain done, it was time to add some steering. I designed the steering using a cheap SG90 servo I got from AliExpress. I used a rack and pinion design to translate the rotation of the servo to a linear steering motion. I designed these gears using a gear from the previous website and a rack design from the website shown here with the settings filled in. I then modified it in SolidWorks to add pegs to connect it into the LEGO. I made a second version with a wider rack to reduce the steering gear slippage between the servo and the rack. A constant issue I had while driving this car was the loose steering, which led to spinouts and rollovers at high speed. I examined the steering system and noticed that there was a lot of play between the steering rack and the wheel arm. As a simple solution, I added some layers of tape to this area to tighten up the tolerance. This reduced the steering looseness significantly. To accommodate my throttle and steering channels, I switched to a 6-channel FlySky receiver. You can see here some of the soldering work I did to connect the 3 pins of the servo to the receiver module. There are 3 pins for each channel of the receiver: signal, power, and ground. I used channel 2 to connect to the throttle of the motor, and channel 4 to the servo steering. Putting it all together, you can see the steering works very well. The grind noise you hear is the servo motor slipping when the wheels are fully turned, which is just due to the SG90 being a cheap servo device. To add some style to this project, I added LED lights that I bought off of AliExpress in an assorted LED pack shown here. Here I added some heat shrink to the white and yellow headlights that I drilled out and glued into the front LEGO pieces. I think the headlight result looks pretty cool. Next, I added a strip of ice blue LEDs to the underside of the car to give it a cool underglow effect. Finally, I cut out slots in the back LEGO pieces and glued in red LEDs to create taillights. To power this car, I used a 1200 mAh 2S LiPo battery that fit snugly inside the driver's cabin. With everything put together, it's now time to take it out for a spin. For this initial driving, I actually used an old LiPo battery I had laying around and taped it to the roof of the car just because it was simpler. Here I also wanted to try out some simple drift tire slicks on the wheels to see how well I could drift the car. You can see the speed on this car is pretty impressive. It's fast enough to roll itself over. With the amount of torque this car has, making it into a drift car is no problem at all. With LEGO, you really need to glue the wheels to make sure they don't fly off. As I alluded to earlier, the steering is pretty unstable right now, which causes the car to spin out easily at high speeds. To remedy this, I added a gyroscope into the steering design. I purchased this simple PWM gyroscope device on AliExpress. The gyroscope functions by measuring the velocity in any of the rotational axes. This module then modulates the PWM to oppose the velocity change and keep the car moving straight. The gyroscope takes the user PWM, applies a gyroscopic compensation, then outputs a compensated PWM to the servo steering. I soldered the 3 wires of the receiver channel 2 output into the gyro input. Then, I soldered the 3 servo wires to the output of the gyro. I tested the gyro function right away by lifting the vehicle and intentionally turning the car side to side, away from the straight position. You can see the gyro turning the wheels in the opposite direction to correct the error and keep the car pointing straight. As a nerd, I find this super cool. Finally, we get to the fun part of driving the final product with the gyro installed. I don't have a speed radar gun yet, although I do plan to make that in a future project. So I calculated the speed of this run by measuring the distance from the concrete support to the camera, which was about 5 meters. Based on the travel time of 500 milliseconds, the car reached a speed of 35 kilometers per hour, or 22 miles per hour roughly, which is insanely fast, and faster than any RC modified LEGO car I've seen on YouTube. With the gyro installed, I'm actually able to drive the car with one hand and no control of the steering. I took the car outside to test it out in another light. Overall, I'm very happy with how this project turned out. There were times when the gears were getting stuck, the controller was burning out, and the thinner axles were breaking, where I thought it might be impossible to actually turn a regular LEGO Technic car into an actually fast RC car. But I iterated on my entire design many times to get to this point, and now it's turned out to be a super fast RC car that can drift while still being the LEGO car I built. It's also just a blast to drive. This was a pretty long project to make and film, so if you liked it, please like this video, and consider subscribing to the channel so I can work on some new cool projects. Thank you so much for watching the video. If you liked it, please give it a like, and if you want to see more of these videos, please consider subscribing. It'll really help get this channel off the ground. I have a lot of cool video ideas in the pipeline, and you're not going to want to miss them.